So we start with today the concept of lattice and unit cell with respect to our discussion on crystalline materials. We will go forward today regarding these two concepts and how do then we will see that these help us in understanding the arrangement of atoms inside a material. And then further our basic aim is to interrelate this arrangement of atoms, which I will say then later on as crystal structure, to the performance and the properties of the materials. So going forward, we today try to define these two terms, the term lattice and crystal, and a few more terms like motif and basis as we proceed further. Lattice is also sometimes referred to as Bravia lattice because you may have already studied that there are 14 Bravia lattices which are available to us, given by the name Bravia because the mathematician who actually said that there are 14 different ways in which points can be arranged in a three-dimensional space, and that is why they are known as the 14 Bravia lattices. Try to define lattice today here. So we try to define lattice here as simply an array of points. So it is an array of points, and keep it in mind that I'm referring to points here. We are not referring to the term atoms for the time being. So I'm not referring to the term atoms for the time being. We are saying here that lattice is an array of points in a space with an understanding that each of these points have got identical surroundings. So whatever points are there, they all have identical surroundings. Second way to define is a more mathematical way. We will try to understand what is the meaning of this today. We say it is a translationally periodic arrangement of points in a space. So lattice can also be defined as a translationally periodic arrangement of points in a space. So again the term points in a space. So this space we say can be a two-dimensional space, or this space can be a three-dimensional space. Both ways it is possible for us to have a lattice. One case it will be called a 2D lattice, and in the second case it will be called a 3D lattice. We will begin our discussion with 2D lattices, and then we will go on to the concept of 3D lattices afterwards. Further, there are other things which can be attached to the basic definition of a lattice, which is most of it is already given here, but we'll still say that because all the points have identical surroundings, that is why any point can be treated as the origin of this pattern. So it's an arrangement of atoms, arrangement of points where each point has got identical surroundings, and any point can be chosen as the origin of the pattern. And these points which have got identical surroundings, they are also referred to, or they are also called as lattice points. So we say they are also referred to as lattice points here. Now, now coming to this figure here, where we find that now what it is? It is a arrangement of points. So we have an array of points. So this is nothing but an array of points, where we are saying that to be called as a lattice, the underlying condition is that this array of points shall be such that each of the points must have identical surroundings. So the points which are here, or a point here, or a point here, anywhere in this lattice, they all shall have identical surroundings. And we find that it is true. If I consider a point A here, or a point B here, or a point C here, if I move a distance A from A, I see an atom here. I see a point here. If I move a distance B here, I again find a point here. Similarly, by moving this distance here toward this side, we find that there are 4 points which are available to us. Similarly, for the point C also the same thing is visible to us, and that is why we say that point A, B, C, D, A, B, C here, they have got identical surroundings. So the points here in this array have got what we refer to as identical surroundings, and that is why this array of points classifies as a lattice. It can be defined as a lattice here. Let us see what. Now there can be different ways in which points can be arranged in a 2D space, and that is how you will call them as different types of lattices. Now how do you know that which type of a lattice it is? For that purpose we need to know something what we refer to as lattice parameters. So what are those lattice parameters? In this case we find here that the lattice parameters here are referred to the two vectors, the vector A and vector B. So the vector A here tells me that if I am at point 1 and if I translate along x-axis by a vector A, I reach at the point 2. That is the second lattice point. Similarly, from point 1, if I translate by a vertical distance b, I reach at point 3, which is the next lattice point. So 1, 2 and 3 here are what we refer to as lattice points. And what are these translation vectors? A and B here are what we call as translation vectors. So the basic definition here happens to be that A and B are the two translation vectors here, and we say that these two translation vectors are what we will be calling them as the lattice parameters. So the lattice parameters here are these two translation vectors as well as the angle between them. So the angle between them, if right now we say, is taken as alpha. So when I combine these three here, we say that these three are what we refer to as lattice parameters. So in a 2D lattice, we need to have three lattice parameters. The two distances A and B, and second is the angle alpha, which is the angle between them. So we find here that we have A and B, which will be later referred to as the lattice vectors or the translation vectors, and alpha angle, which is the angle between A and B. We call them as translation vectors because we reach from one lattice point to the second lattice point by translating through these vectors. By that reason, somebody can say that this also happens to be a translation vector. Means I can reach from here to here also by a second lattice vector. That means this also can be treated as a translation vector, and we will see later on that why we say that. Now, there is one more concept. This is so far as the lattice is concerned. The second term which we'll add here is what we have written here as motif or basis. Now, what is a motif, or also known as a basis? So right now I am saying here that this is lattice is nothing but an arrangement of points. But in our discussion about crystalline materials, we say atoms. So there are atoms which are arranged here. So when I say lattice here, it is an arrangement of points. Now at this point, so there are a number of points that we find here that we call them as lattice points here. This point, the other point, and the other point, whatever lattice points are there, what is located at these points? So we say that what is located here is what we call as the motif, or also called as the basis. Now motif or basis here can be what we refer to as one atom or a set of atoms, or more than one atoms, or or a set of atoms. So in a way, what I'm trying to say here is that lattice is telling me that how these points are placed in a two-dimensional space. How these points are placed, that means how far they are, they are defined by two translation vectors A and B, and angle alpha is the angle between these two translation vectors, whereas motif defines that what is placed at these points. Whether there is a single atom placed at these points, there may be a single atom which is placed at these points, so then that atom may be called as a motif here, or there may be more than one atom placed at each point, each lattice point, and that is why we call them as then a motif or a basis. The thing will become more clear in the next slide. So what we see here is this. So what we see, right now what you are seeing here is the arrangement of atoms in a graphene sheet. This is a graphene sheet, which we say what it will be. It will be a number of, it's a set of carbon atoms and then how they are arranged. So if you look at this figure here, what is observed is that the black one here are all carbon atoms. These are the carbon atoms. And what is the periodic arrangement? At the first instance, it looks like that it is a hexagonal arrangement. So if you look at this, it looks like that it is an hexagonal arrangement. But if you now try to see that whether this hexagonal arrangement, this one, this defines the lattice, whether this is the lattice or something else is the lattice. So to see what it is. So if I treat it as this one, if I take out one of these points here and one of the hexagons is taken out, let us see. So let us say we are here. So try to recall, how do you define lattice in our discussion? We say it's an array of points such that each point has got identical surroundings. So the surroundings must be identical. So going by that concept, if I look at this point, which is point 1, the surroundings are here. It has got 2 points which are available to me here. When you look at the second point, it has got again this arrangement here. But when you look at this point here, and when you look at the second point here, this point and the second point, we find that this does not define a lattice. They do not have what we refer to as identical surroundings. So then what is the lattice here? So now if you look at, with this discussion, when you look at this figure here, we find here that the lattice here is this. This means now the lattice points are 1, 2, 3 and 4. And how it is translating? It is translating like this. This is how it is translating. I hope you are getting what I am trying to say. So we find that this is how they are translating here. Similarly, we will see that this is how it will go to the next point. And so So the underlying lattice happens to be this lattice, which we will later on say that this is called a hexagonal lattice. Then what is the motif? What about these points? What about these atoms? So now we say that what is the basis? We are now saying that the lattice point here are these. This is the lattice. And what is there on each point? On each of these lattice. So these are the lattice points. 1, 2, 3, 4, 5, 6. These on each of these lattice points we have placed a motif or a basis. So just recall that what was a basis? A basis can be a single atom or a set of atoms. So here we have placed a set of atoms, means that each of the lattice points we have placed two atoms. One is here and the second is attached here. So this is the motif. So on every lattice point I am placing a motif which is a two atom motif here like this, and this is how then it becomes. So on each of the points what we are doing, we are placing a motif here. So a motif here happens to be a set of two atoms. So it happens to be a set of atoms. So this is the basic understanding of what we refer to as a motif or a basis. So just to repeat that again, a lattice happens to be an arrangement of points. What is located on these points is given by a motif or a basis. When we refer to crystal structure or a crystal lattice, then we say that in place of those lattice points we have located atoms or maybe a set of atoms. If for pure metals we say this is nothing but the single atoms themselves which are located on the lattice points. And in many of the alloys or compounds we will see later on that there may be what we refer to as a set of atoms which are placed, which may be of same type or of different types. Right now what we are seeing here is the atoms which you see here are of same type. So this is also a carbon atom, this is also a carbon atom. So what we have placed is that on each of the lattice point two atoms are placed, 1 and 2, and this is why it is referred to as a motif here. Okay, then try to define what we refer to as a unit cell. Let us see how do you define a unit cell. So trying to define unit cell here, we will then refer to that what are various types of unit cell. So we'll be having discussion about primitive unit cell and a non-primitive unit cell. It is very important to understand the difference between these two types of unit cells, the primitive unit cell and the non-primitive unit cell. But before going to the definitions here, let us see how do you define a unit cell. So what is a unit cell? So we say a unit cell of a lattice or a crystal structure is a unit such chosen so that it is space filling. So it is space filling. So the meaning of it will become clear in my next slides here, that why I am saying it must be space filling. It must be space filling, and what else is there? Sorry. So it must be space filling. And the second important thing is that once it is translated regularly, it must build the entire structure. And then we define primitive unit cell. There are a number of definitions of primitive unit cell, but we will give you 2-3 definitions which are conveying the same meaning but slightly in a different way. To begin with, the basic definition happens to be the primitive cell happens to be the smallest unit cell, which also opens up an point that the unit cell may not be a unique. So a unit cell is not a unique one. Means you can create a lattice or a crystal structure with unit cells which are of different shapes, but they still satisfy the criteria that they are space filling. And the second one, that once they are translated regularly, they will generate the lattice or they will generate the crystal lattice. So I define two terms here in my discussion here. The lattice, which we have already defined, an arrangement of points. And if I say it is a crystal lattice, now what I have done is that on each of the lattice points we have placed a motif or a basis. Means now on these points we say that we have placed maybe a single atom or atoms. Now these atoms may be of same type or of different type. So we define a unit cell, and then going forward to the definition of the primitive unit cell and the non-primitive unit cell. So to begin with this, let us see that when I look at this arrangement, we find that this can be one unit cell. This can be one unit cell, because if you try to recall this definition here, it says that the unit cell of a lattice or a crystal structure is the unit such chosen so that it fills the space, and once it is translated regularly, it builds the entire structure or the entire lattice. So we see here that if this is the unit cell and if I translate it regularly, this is able to give, this is the space filling one, and this is also able to give me a complete lattice. So complete lattice can be generated by this concept here. Okay, so this happens to be completely defining or an example of a unit cell. Now this unit cell can be of a lattice if it is only points, and if the unit cell can be of a crystal lattice if there are atoms placed at these points which are there. But as we already said that the unit cell is not a unique one, means I can generate the same lattice by a second unit cell. Let us say this one. So the unit cell can be generated this way also. So then what shall we call this type of lattice as? As we said, there can be different types of arrangement of points, and if I call this as a rectangular lattice, I may not be correct, because the same arrangement of atoms, that the arrangement of points that you are seeing here, can be generated by a rectangular unit cell as well as maybe not a rectangular, maybe a parallelogram type of a unit cell. So this gives me one idea that normally when you are referring to unit cells we are saying that the type of the name of the unit cell is given by the shape, whether it is a rectangular one or a cubical one, and we say if this is that is known as that particular crystal structure. But right now what we are seeing here is that a unit cell, a rectangular unit cell as well as a non-rectangular unit cell, both of them are able to generate the same lattice. And we can have a better one. We can have, let us say, this one also. So this is also then a bigger one. This also is a unit cell. So this is also a unit cell. Or then somebody can say that this is also a unit cell. So this is also a unit cell. So there are different ways. So it's not a unique one. Then, so this is one concept, that the unit cell is not a unique one. The second is now the concept of primitive and non-primitive unit cells. So we said that there are two types of unit cells, primitive and non-primitive. One definition, we said that the primitive one happens to be the smallest unit cell in a lattice. There are better ways to understand it, and there are better definitions that you say. One of the definitions which says is that primitive unit cell has lattice points at corners only. A primitive unit cell is that unit cell which has got lattice points only at the corners. One more definition can be there, which is available again in number of texts, that a primitive unit cell is such a unit cell which has got only one point in it, one lattice point, only one lattice point in it. What do you mean by that? Only one lattice point means if this is the unit cell which I am referring to, it has got lattice points only at the corners. So it has got lattice points only at the corners, 4 corners in a 2D one, and the points which are at the corners, they are shared on all the sides by 4 other ones, and that is why the number of lattice points in this unit cell happens to be 1. If we then go, if you say that you take it to a 3-dimensional one, so it may become a, let us say, a cube in that case, which has got 8 lattice points, but all of these lattice points at the corner of the cube are shared by the other ones, and that is why the lattice point which is there, complete lattice point which is there in a primitive unit cell happens to be 1. So this is what defines as a, so this one will be what we refer to as a primitive unit cell, which we will say with letter P later on, which then tells me that this unit cell is not a it's not a primitive unit cell, so it is a non-primitive unit cell. This one also happens to be a non-primitive unit cell because this has got lattice points not only at the corners but at other locations also. It has got the here also, it has got here also. In this case also, this unit cell has got lattice points not only at the corners, but there is another lattice point here at the center. So this happens to be the non-primitive unit cell of the same lattice. So all of them represent the same lattice that you are seeing here, whether this is this type of the unit cell, whether the unit cell is this type. Now What about this one? This one will also be a primitive unit cell, because again this has got lattice points only at the corners. So this has got lattice points only at the corners. And when you see that whether it complies the definition of a primitive unit cell, it does, because we said that it must have lattice points only at the corners and it must contain only one complete lattice point in it. So that way we say that that's the basic difference between what we refer to as the primitive unit cell as well as the non-primitive unit cell. Okay, now coming to a three-dimensional one here. From a two-dimensional lattice, let's go to a 3D lattice. Right now again I'm referring to only lattice here. The blue ones, they are again the points only. We are not referring to them as atoms for the time being. So we say a lattice is made up of a unit which repeats itself, which we say is called as a unit cell. And in the case of a 2D lattice, we said there were two translation vectors and one angle between them. In the case of a 3D lattice, now we say there are three translation vectors. The translation vectors here are, or the lattice vectors here are A1, A2 and A3, which we call them as the basis vectors. Basis vectors. That means the basic understanding is that when you move this much distance in x direction, this much distance in y direction, this much distance in z direction, you will reach the next lattice point. So the basis vectors here are given as A1, A2, A3, which are also known as the lattice parameters of the unit cell. And we define the three angles here, alpha, beta and gamma, such that alpha here is the angle between A2 and A3, gamma is the angle between A1 and A2, and beta is the angle between A1 and A3. This is the standard notation which goes as far as crystallography is concerned. So we say that a 3D lattice is a arrangement of points in a three-dimensional space. Again, it must be space filling, and each of the points to be called as a lattice point must have what we call as identical surroundings. And this is how we say a 3D unit cell of a lattice will look like. We will call it as a lattice if I consider this as only points. But if I say that on these points we have put atom here, then I will say that this happens to be then the crystal lattice. If it is only point, we say it happens to be only the lattice. So that's the basic difference between the term crystal lattice and lattice. So what we have done in this lattice, we have added the motif or the basis to make it as a crystal lattice. That's very easy to understand. A primitive unit cell we already defined is the one which contains only one lattice point in per unit cell, and it is given by the term P here. And this is what we see, that once it repeats in 3 dimensions, it creates a space filling structure. And this is how it creates what we refer to as, then if these are all points here, this is what we say, it creates what we call as a crystal structure. Okay. We said a unit cell must be space filling. These are some of the examples. We say that I have, let us say, a cuboid, and I want to divide this total space into identical building blocks, which we say will be termed as unit cell in our description here. They must be geometrically regular, and I must only use a single type of blocks, so that to be very clear regarding that what will be a unit cell look like. So I can say that this one can be broken down into these small cuboids, such that the smallest one, this happens to be let us say the unit cell in this example. It is a space filling one, a repetitive one, and it satisfies both the criteria. It is repeating unit and it is a space filling unit. Now there are other possibilities. I can do the same exercise and then create a unit cell like this, or I can do the other exercise and then create from here I may create this as a unit cell here. So this is also one example. This is another possibility that this can be the type of the unit cell here. There's another possibility that in place of that one, now I can create that these are 8 faceted elements here, and then this can be one. Or somebody can say that why not hexagonal one? So we can have a hexagonal one here, which we say that these can be there, and then you are creating a space filling one. This means this still happens to be a space filling one here. Now the hexagonal one which you see here right now, it can be, when you look at it, it can be broken down into two ways. We can break it up. We can say that this hexagon can be broken into 2 parts here, or the complete hexagon here that you saw, this one, can be broken down into these 3 ones. This is what you observe here. 1, 2, and the 3 one here. So it can be this way or this way. Now which one shall I do? Keep it in mind that to create a lattice, a unit cell must be space filling, and it must be periodic. It must be keeping the same orientation here. So if I treat this one here, I find that I create this one here. I put them in translations. If I translate them along this axis, this is not space filling, so there are voids which are contained here. I can make them space filling, but then the orientation has to be changed. I need to keep them in 2 different orientation. Whereas it is better that I keep them this way. So if I keep them this here as a unit cell, we find that this satisfies the criteria for the definition of a unit cell, which we say must be space filling as well as repetitive in nature. So that is how we can say that there was one example where we find that how you can understand that what is the significance of the shape of the unit cell.